Here we've produced a video that shows some of the under-the-hood predictions for the main camera that is facing forward on the car. And you see that we're detecting lanes, we're detecting stop sign over there, a stop line, road markings, we're putting cuboids around cars, traffic lights, road edges and curbs, even things like trash bins coming up over there.
Hey guys, and welcome to a new video. In this video here, we're going to talk about Tesla's AI and full self-driving system that they're currently developing. So in this video here, we're going to see Andrej Karpathy's view and the different kind of approaches that Tesla uses to solve this full self-driving cars here. So we're going to see the different kind of approaches they take, and Andrej Karpathy is going to explain some of the things and the approaches that Tesla takes throughout this video here. But first of all, remember to join the Discord server. I'll link to it down in the description here, and you can come chat with us about deep learning, artificial intelligence, computer vision, and stuff like that. And also, if you have some problems with your project, you can get your questions in there, or just come chat with us. You can now also be a member of the channel here if you want to support the channel with a small monthly fee, and everything will go to create more and better quality content here on the channel.
So in particular, we take a heavily vision-based approach. So everyone else has a LiDAR on the top of the car. The LiDAR shoots out lasers and creates a LiDAR kind of point cloud map. And then you pre-map the environment that you're going to drive. So you have a high-definition LiDAR map, and you localize to it to a centimeter-level accuracy. And then you know exactly the path you're going to take, so you can just steer to keep yourself perfectly localized in the correct region. So this is quite helpful, but this is not the approach that we take. We do not have LiDAR on our cars, so we don't shoot out lasers. It's all camera-based. And we do not build high-definition maps. So when we come to an intersection, we encounter it basically for the first time. We come to an intersection, how many lanes are there? Left, right, center, which way should I turn? What are the traffic lights? Which lanes do they control? All of this is just done just from camera feed, camera vision alone.
So what Andrej talks about in this short video clip here is that Tesla uses a pure vision-based approach to actually solve full self-driving, where other companies like, for example, Waymo, they're using these LiDARs that he talks about as well. So they're actually driving around in the environment, creating these high-definition maps. So they're actually driving around, pre-mapping the environment, so they know where all the obstacles are, like the road signs, the traffic lights and stuff like that. So they actually pre-map the environment, so they know everything about their environment. But Tesla is not using that approach. They don't have any LiDAR, they don't have any high definition maps. So you can just place the Tesla car and you will just drive around based on pure vision that they're taking. So they're not using these laser beams here that is thrown out. So they take the more kind of approach like a human, where we have two eyes that is driving around the environment, and then they're using perception and this pure vision based approach to actually solve full self-driving.
So here's a random scene where we have to potentially drive and wind our way through this scene. As a human, this is relatively effortless, but you're actually doing a lot under the hood, and the autopilot has to as well. So we have to understand a lot about what are the static objects, what are the dynamic objects, what is the road layout, what is all of the layer of semantics on top of the road, like lane line markings, road markings, traffic lights that tell you about how you can actually traverse that scene. So once you actually start writing down what's necessary to actually perform the driving policy, you end up with a long list of tasks, all of which we need to actually handle. And the detection of these tasks serves two purposes and two customers. Number one, we actually need it for the driving policy. And number two, we actually want to show a lot of things on the instrument cluster for the human so that they gain sort of confidence in the system. Here we've produced a video that shows some of the under-the-hood predictions for the main camera that is facing forward on the car. And you see that we're detecting lanes, we're detecting stop sign over there, a stop line, road markings, we're putting cuboids around cars, traffic lights, road edges and curbs, even things like trash bins coming up over there, lines that make up the intersection. In a bit, there's lines that create parking spots. We have to have all these attributes for whether or not a line is for a parking spot or not, and things like that. So these predictions look pretty decent, but it's actually a huge amount of work to get them to actually work at scale and in the full long tail of what you can encounter on the roads.
So what Andrej talked about here in the last video is actually all the different kind of tasks that the car has to detect while driving around in the environment. So we saw that the car both had to detect the traffic lights, moving objects, signs, different kind of road markings, lane lines, road signs, and also static objects in the environment. So when the Tesla car is actually driving around in the environment, it has to detect all of these different kind of information, or important information here for the car to actually operate in the environment by itself. So Tesla is actually using something called a HydroNet, where it actually has a kind of a backbone, and then on top of that backbone, they have actually built individual neural networks for detecting these different kind of objects or the different kind of tasks that they want to detect while the car is driving around in the environment. So I'm going to dive more deep into like what HydroNet is and how we can actually like use that, where we have like a backbone in the HydroNet, and then on top of that we have actually like individual neural networks. So make sure to subscribe to the channel here and also hit the bell notification so you know when I upload that video where we're going to talk about different kind of like neural network architectures that we can use in the backbone of the HydroNet architecture, and then how we can actually like stack neural networks on top, or like modules on top of that HydroNet or that backbone to actually like solve these different kind of like detection problems, or these different kind of like solving different kind of tasks that the car has to do while driving around the environment. At the end of the video clip here, we saw like what the Tesla actually like sees when it's driving around in the environment, and we can just see all the different kind of things, like for example like lane lines. They're actually like trying to predict out in the future what the lane lines are actually going to do, and they're going to predict the curves off the road. And we can also see the different kind of like cars. They're actually like detecting or estimating the distance towards the cars driving in front of us, and also the stop signs and stuff like that. So a lot is going on in the cameras and also in the computer when the Teslas are driving around, and we can see all the different kind of tasks that they're trying to detect while driving around. We can also see at like the images and what the camera is actually like seeing is how much it actually like has of visibility. Like for example, if it's raining or if there's fog and stuff like that, then it also takes that into account, and it has like a probability of like how much the camera can actually like see when driving around in the environment. So this pure vision based approach that Tesla is taking is just really amazing, and we can see like there's a lot going on in the car when it's driving around, and they can actually like see a lot more than the actual human. And as we saw in the video clip here, those are actually like only the front facing cameras. The Teslas actually like have 8 cameras that is around cameras, so it can see like 360 degrees around the car. So that's really nice, and all of the different kind of cameras are detecting different kind of objects and solving different kind of tasks, and then they're actually like combining all of those together, and then the car can drive it around with surround cameras and detecting these different kind of objects and solving these tasks to be able to solve full self-driving.
And so I've shown in the Autonomy Day presentation earlier last year the data engine, the process by which we iteratively apply active learning to source examples in cases where the detector is misbehaving, and then we source examples in those, and we label them and incorporate them into part of a training set. So for stop sign detection, as an example, we have a approximate detector for stop signs based on an initial seed set of data, and we run that and deploy that to cars in shadow mode. And then you can detect some kind of a lack of health of that detector at test time. So for example, the stop sign detection is flickering. That could be a source of uncertainty. You can also detect that the neural network is uncertain in a certain Bayesian way, and there's a few ways to model that. You can find instances where you get surprised to see a stop sign, like why didn't you see it when you were a bit further away? You can also source examples when we detect a stop sign, but the map thinks that there should be no stop sign, or vice versa. So sort of a map vision disagreement. So we have lots of different ways of sourcing difficult cases, and then we upload images and we look through them, we label some of them and incorporate them into a training set.
So in this video clip here, Andrej talked about the data engine of the Tesla car and how to actually like use this data engine here to actually like gather new data. Then after they have gathered the new data here, they're actually like going to label them. They're using some different kind of techniques. They're both using manual labeling, but they're also using some other different kind of techniques that he talked about here. And then they're trying to use some more self-supervised learning, so they're actually like labeling itself. So when the data has been labeled, it actually like goes into the data set of all the different kind of images that they have. And then they can actually like retrain the whole neural networks, or like the HydroNet that they're using, or the neural network that they're using for that specific task, solving that specific task. Then they can actually like train that neural network on the new data that they have now gathered and they have been labeled. And then after they have trained that neural network, it can actually like deploy that trained neural network on the new data to the car, and then the car drives around. It gathers, it generates, and it creates like more data examples. So it creates like new data that now needs to be labeled. And then after it has been labeled, it just goes into the neural network again. And then we have this data engine loop here, where we just have these different kind of like cool features here, where the car is driving around, generating data. We label the data, we feed that data to the neural network, we train the neural network, and then we deploy that data, or like that model that we have now trained, to the car, and then just goes forever and ever and ever in this loop here. So the more data, the more cars driving around, the more data Tesla gets, and the better the neural network and the better the full self-driving vehicles are going to be.
We have to know a lot about any scene, and each one of those things has their own data engine. So what we end up doing is we have these neural networks that have a shared backbone, and then they're multitask, juggling lots of different tasks. And in total, the team is currently maintaining 48 networks that make 1,000 distinct predictions. These are just the raw number of output tensors. If you just take all of our networks and you add up the output tensors, it's 1,000. And those tensors, of course, can have multiple predictions in them. None of these predictions can ever regress, and all of them must improve over time. And this takes 70,000 GPU hours to train all of the neural nets. If you have a node with 8 GPUs, you will be training for a year.
So Andrej just showed an example here of the HydroNet architecture that they're using to solve these different kind of tasks or an individual task here when the car is driving around in the environment. So we have this shared backbone here with a neural network architecture that we're going to talk about as well. Tesla is using ResNet as their shared backbone, and then they're just doing the feature extraction in that backbone, and then they're actually doing the object detection or solving the individual task in the modules built on top of that backbone. So they have this HydroNet architecture here where they had these objects here as a module on top of that backbone. And they also had a neural network to detect traffic lights and also markings like lane markings and stuff like that. So in total, they have 48 neural networks running on top of this shared backbone here in the HydroNet architecture. And these 48 neural networks here are actually for solving each of the individual tasks here when the car is driving around. So an individual task could, for example, be detecting stop signs, traffic light control, objects like, for example, cars, pedestrians, stuff like that, and also lane markings and lane roads. So we also saw that we have 1,000 distinct predictions for each pass through the neural network. So they have a lot of predictions, and we saw that when the car was driving around, and Andrej showed what the Tesla sees when it's driving around in the environment with their cameras, and it takes 70,000 hours or GPU hours to actually train this HydroNet architecture here with the 48 neural networks built on top of that shared backbone.
So what I've explained so far is you take an image from one of the cameras, you run it through this shared backbone, and you make lots of predictions about it in the image pixel space. So we can potentially predict objects, lines, or edges, and so on. Taking the example of edges, where does this go afterwards, right? So here's a video, and I'm showing the predictions of the road edge task on all of the different cameras. And you can see that this is basically a binary segmentation problem for us. And we detect those edges here, and we use this to wind our way through a parking lot because we'd like to go to a certain destination but avoid all the road edges. Now, you can't just drive on the raw predictions of these edges in these two-dimensional pixel pixel coordinate systems. So you have to somehow project this out into a bird's eye view in order to make this make sense. So the raw detections, we project them out into 3D, and we stitch them up into what we call a occupancy tracker. So this occupancy tracker takes all the raw measurements from the 2D images, we project them out into the world, and we stitch them up across cameras, and we stitch them up across time. So the occupancy tracker is keeping the temporal context of that, and it creates a small local map, and then it winds its way through this parking lot to get to the person who is summoning the car at this time.
So what we just saw in that video clip here is actually really amazing, where the Tesla is driving around, it's having the surround cameras, 8 cameras around the car, predicting road markings and stuff like that, and then they're actually combining all the different kind of predictions from all 8 cameras for all 8 surround cameras. And then they're actually combining those predictions to create this bird eye view here over the car, so they can actually create an environment or a map where the car can actually drive around. So this can actually be some kind of high definition map as the LiDAR scanner could do. But Tesla is using this pure vision based approach here, and as we saw, we can actually have this map where the car is driving around. It knows where every edge of the road is, and also the lane markings and stuff like that. And then it can actually just drive based off that.
So a lot of our networks have been moving towards these bird's eye view network predictions, where you take all these cameras and you feed them through backbones, and then you have neural net fusion layer that stitches up the feature maps across the different views and also does the projection from image space to bird's eye view. And then we have a temporal module, potentially, that actually smooths out these predictions. And this is all neural net components. And then we have a BevNet decoder that actually creates the top-down space. And so then we can directly, potentially, predict these road edges in a top-down view. Now, this makes a huge difference in practice. So here's an example. In top row, I'm showing the left camera, center, right. And I'm showing road edge detections in red. On the bottom row, on the left, you see the ground truth of what this intersection looks like. And you see that the car is positioned on the dot. And so that's the ground truth. On the very right, you see what happens when you take 2D predictions in the images and you cast them out. You basically get garbage. It somewhat works around the car. There, the projection is easy. But far away, especially near the horizon line, a few pixels of error means lots of meters of error. And so these projection-based techniques are extremely hard to get to work. You'd have to know extremely accurate depth per pixel to do that projection. It's a very hard problem. And in the middle, you are seeing some of our predictions from the recent bird's eye view networks that just kind of make these predictions in top-down view directly. So let me show you a video here of what this looks like in practice. On the top, we will have a video of an intersection. On the bottom, I'm showing some of the predictions achieved by the Tesla AI team that has produced these bird's eye view networks. We have road edges in red. We have dividers in green on the very left. Then we have attributes for these dividers. So we want to know if it's an actual curb or if it's just like a logical curb, so like a yellow line or something like that. And then we have a traffic flow direction and a few other things like that. I'm only showing some examples. But the car is on the bottom center of these images. And as we're turning through this intersection, these bird's eye view networks just predict pretty far away the full structure of this intersection and what it looks like. So this is extremely powerful for us.
So Andrej actually showed here an example of like how what the car sees when it's driving around with this bird eye view predictions here. So he showed like how the different kind of cameras actually like fuse together, and the predictions from those cameras is actually like fused together. Then they're using this BevNet here to actually like do the predictions of the individual like objects, road line or road edges, and then we can actually like see the bird's eye views predictions from that neural network or like from that BevNet. And then at the end we saw an example of like different kind of like in the importance of using this bird eye view predictions approach here instead of just making these 2D predictions out to 3D predictions, because we don't really have that much information when we're going into like the horizon in the image about the depth of individual pixels. So it's really important that they're using this bird's eye view here, where they're first making this bird's eye view prediction here, and then the actual prediction, projecting out the 2D points that they're detecting in the images to the actual like 3D points in the world coordinate system. So this is really important to be able to predict where these different kind of like road edges are in the real world coordinate system. So if you want to know more like how these different kind of neural networks here work, make sure to check the videos out I've made in the deep learning tutorial here on my channel, where we talk about like the basic stuff about neural networks, convolutional neural networks, how we can actually like do these different kind of predictions and classification problems. And then in the later videos and future videos, I'm going to talk more about like different kind of neural networks architectures, like ResNet that Tesla is using, and also some different kind of other architectures that we can use. And we're going to dive more deep into the actual like hydrated neural network, where we have this backbone, and then we have individual neural networks or like modules built on top of that to solve these individual tasks here, because this is really crucial for being able to solve real life problems with neural networks, and also like real life problems where there's a lot of different kind of individual tasks that is really complicated, and it gets really confusing when we're combining all these different kind of tasks here together.
Here's an example of using this for objects. So on the top, we have our camera feeds. On the middle, I'm showing our per pixel depth predictions achieved via self-supervised learning. We need those depth predictions because we take, as many others do in the literature right now, we take a pseudo LiDAR approach where you basically predict the depth for every single pixel, and you can cast out your pixels, and you basically simulate LiDAR input that way, but it's purely from vision. And then you can use a lot of techniques that have been developed also for LiDAR processing to actually achieve 3D object detection. So on the bottom, you have then predictions of our detector directly in the bird's eye view. Yeah, here I have one more slide showing just our depth predictions for some other videos. This is not very exotic for any of you who are in computer vision, because there are entire workshops and creating videos like these where we are basically achieving depth directly from images. And this is done, of course, no human can annotate depth. So this is done using self-supervised techniques. So in particular, we take an image, we predict a depth. Then when you have a depth for an image, you can cast out all the pixels into 3D, and you can reproject them either into camera views at that same time, but different cameras, or you can reproject them into the future frames of that single camera. And then you have a photometric loss that's enforcing consistency. And so the only way to predict, to make everything consistent in reprojections is to predict the correct depth. And so this learns in a self-supervised fashion to predict depth, and then we can simulate LiDAR inputs directly from vision and use this downstream to make these bird's eye view predictions.
So what Andrej just showed us here is really crucial for being able to solve full self-driving, because when we're driving around in the environment, we actually like need to know the different kind of like depth or the distance to different kind of individual objects, or different kind of like stop signs, cars in front of us and stuff like that. And they're actually like doing these depth predictions here, or like as we saw in the video, we saw these depth maps here that they're creating with these self-supervised learning techniques here, because they actually like have individual cameras that is seeing the same thing in the scenes, so they can use that to actually like create a depth information about the image. Because if we only have a two-dimensional image and we only have like a monocular camera looking out, we don't have any information about the depth. But when we have two cameras looking at the same different kind of like objects, we can actually like calculate something called a disparity, and then we can create the depth maps from disparity. So if you're interested in how we can actually like use stereo vision or like stereo camera setups where we actually like have two cameras, because when we have two cameras, we actually like have information about the depth of individual pixels or objects in the image. I've also created a computer vision tutorial about that, so make sure to check that out if you're interested in knowing like how we can actually like create these depth maps here and the disparity maps, so we can calculate the depth or the distance to the individual objects in the frame or like in the world, because this is really crucial when we're driving around in the environment, when we're not using LiDAR, because then we don't know the distance to the cars driving in front of us, or like pedestrians on the road, or like stop signs and traffic lights and stuff like that. So we need to know the different kind of like distances to those objects, so we know like how far they are away. And then Tesla using their neural networks to actually like this self-supervised learning techniques to create these depth maps here, so they actually like can go in and use each individual pixel in the depth map to see like the depth or the distance to an object that they're tracking in with their cameras and with their neural networks as well. And then we also saw the different kind of predictions in the real world, like if they're actually like hitting the true labels, or like they're actually like estimating the distance to those objects correctly. So this is a really nice and really important approach they're taking, and they're actually like approaching a really good accuracy and result compared to LiDAR. So they're getting closer and closer to LiDAR, but with just this pure vision approach. So it's really nice, and these neural networks are just fed with images, and they can just predict depth by having these surround 360 degrees cameras around the cars. They're driving around, they're detecting these different kind of objects, and then they're also creating these depth maps here, so we can actually like detect or like estimate the distance to each of the individual objects that they're actually like detecting as well. So we have a 3D world coordinates of each individual object or each individual pixels from the cameras, from like the surround cameras around the car. So this is really important. And this is the way that they're going to solve full self-driving cars, by just using pure vision. They can estimate the depth to individual objects, they can track different kind of objects, and they can do all of these individual tasks here at the same time for each frame, or like for each time the camera is actually like fed or like passed through the neural network. So this is really nice, and they can actually like discard LiDARs, and they can just use this pure vision based approach here instead, and then just feed all the images through the neural networks, do these bird eye view predictions, and then they can create these depth maps here, combine all these things together, and then they can just drive around the car autonomously. So that's it for this video here, guys. We've been over like Andrej Karpathy on the AI that Tesla is using, and they're really using some really nice and cool techniques and approaches that they're taking. They're really like the first movers. They're like improving day by day by just gathering data that we talked about with the data engines. But in this video here, we went over like some more detailed stuff under the hood. So they use some different kind of neural network architectures. They have modules built on top of that for individual tasks. They create depth maps. They create depth eye views, and they combine all of these things together here to actually like be able to solve full self-driving. They can just put the car in the environment, it can drive around based on pure vision. So this is really nice approaches, and they're just like taking AI and deep learning and neural networks to the next level. So thank you guys for watching this video here, and remember to hit the subscribe button and bell notification under the video here. And also like this video here if you like the content and you want more of these different kind of videos here in the future. So I'm currently also doing this deep learning and computer vision tutorial that I've talked about throughout this video here as well. So if you're interested in going more into depth with some of the approaches here with computer vision and deep learning, and know like the basics of those, make sure to check those tutorials out. I'll link to one of them up here, or else I'll just see you next video, guys. Bye for now.